Okay. Next, I'd like to talk about what's called the photoelectric effect. But before that, I just want to kind of review our E&M radiation spectrum. So remember that we have low frequency electromagnetic waves and they get to higher frequencies. This is giving you a size of their frequencies and their um, energy as it goes up. You can see the wavelengths of the objects going down, frequency going up as you go from the low energy to the high energy. And somewhere in here are your visible light waves, really small. Now, the visible light is really a small part of the whole spectrum. Kind of see it over here. It's this little tiny part of the whole spectrum that we have looked at. We've studied light and we say, hey, it's a wave, right? We've seen it's got frequency and wavelength, so it must be a wave. We've observed it. We've seen this diffraction and this interference phenomena. Interference is something waves do. Objects don't do that, right? So we're pretty much saying, hey, light is a wave. But, and wave theory of light is supported by the fact that it refracts, reflects, interference patterns, diffraction, all the stuff that waves do. Objects, particles don't do those things. And then came along the photoelectric effect. We found that if we shine UV light on zinc, electrons shoot out. It's almost like you shoot a particle in and it shoots a particle out. A wave is going in. Is it a wave? It's shooting particles out. The emission of electrons only happens when the light is being shined. Otherwise, there's no electrons just popping out of the zinc material. And it's also found that it's only when you reach a certain frequency of light that the zinc particles or the electrons start getting emitted from the zinc particles. And if you go below a certain frequency, nothing comes out. So it doesn't matter if you add more photons. If the frequency isn't enough, then it doesn't knock the electrons out. It means it requires a certain amount of energy before it will knock the electrons out. And that's behaving more like a particle where something goes and collides and pops something out. Waves aren't supposed to be doing that. So they came up with the particle theory of light, and that's a photoelectric effect. It's a phenomenon when light shines on metal, electrons are emitted. This supports a particle theory for light. So what is light? Einstein said, light was made up of, these packets of waves, and they carried an energy, and the energy was equal to some constant called h, which is called Planck's constant times the frequency. So we've learned this already, that the energy of a electromagnetic wave depends on frequency, and here's the equation for it. So Einstein's saying, I propose that it's is like a different type of thing happening here, and we think that this is more like a particle. So what's the thing here with light? Is light confused? Does it not know what it is? And then we come to this phenomena called the wave-particle duality. It's a really weird picture, but it says that a light, for example, sometimes behaves like a particle and sometimes behaves like a wave, and not the same way both times. So it's either acting like a wave or as a particle, but not the same at the same time, not both at the same time. That's pretty weird. It gets even more weird. It turns out that particles can act like waves when they're really tiny particles. And they're supposed to be particles. I mean, what's going on here? And so that's what's called the wave-particle duality. So first we say, hey, is the electron a wave or a particle? Electrons, we know, is a particle. It acts like a particle. We've known it to be a particle. But yet you can use electrons and do diffraction with them as well. And they too interfere. And they're like, what's going on here? And so that's the wave-particle duality, which says that particles and waves act like both particles and waves, and not like both at the same time. That is quantum mechanics. It is one of the phenomena that we have to kind of say is